Fred Adams. So in addition to this being the regular Origin seminar, Fred is visiting as part of the TAP, I think you all know, Theoretical Astrophysics Program, Planet Information Initiative. So he'll be here all week. If you got the email for this talk, there's a schedule. There's still times available to sign up. It wasn't so full, so I had a nice leisurely hour already chatting with Fred this morning. It's very enjoyable. And so he'll also be giving talks at our group meeting Wednesday at 1, and then
5:50.
In Stewart 550, and then I'll be giving the astronomy colloquium on Thursday. And so, well, so I don't think Fred needs much of an introduction, but I'll give a little bit of one anyway. One thing we share in common is that at different times we got our PhDs at Berkeley, working with our thesis advisor, Frank Hsu. From there, Fred went on to great things. He did a postdoc at CFA and then was hired as a faculty member at Michigan, where he's been most of his career. Fred's honors include the Trumpler Award, the Warner Prize, and numerous teaching distinctions at the University of Michigan. And so we're honored to have him here today and hear about some of his latest work.
Okay, well, thank you, Andrew, and all of you for inviting me and showing up today. Thank you. So today I'm going to have a pretty ambitious goal here. I want to tell you about the last throes of the planet formation epoch and how you get from there to the distribution of planetary masses that we see. And that's quite a long way to go, so better begin. Okay, so here's the outline. The first thing I'm going to do is give you a brief observational overview of the picture for planets. Many of you know this. I understand not all of you do, so I'll be quick about that. I'm going to make the distinction between the top-down and the bottom-up theories of planet formation, and then I'm going to dismiss one and focus on the other, and you'll see what I do that. See how I do that. I'm going to give you a brief overview of the core accretion paradigm, which is the bottom-up scenario. And then most of the talk are the last two pieces. I want to develop a completely analytic treatment for the last stages of the core accretion paradigm when most of the planetary mass is assembled. And that will culminate in a way to calculate the spectral energy distributions of these things, so you can actually see what they look like when they're forming. And then I'm going to use all of the pieces to calculate or to begin the calculation of the theory for the initial mass function for the planetary mass function. So we'll see how far we get. Let me begin by acknowledging my collaborators. Arthur is not in any way related to me, but his name does appear on one of my papers. So this is the observational overview of planet formation or planets. These are all the exoplanets we found as of a couple of years ago. They're color-coded by the way in which they were discovered, but you see they span many ranges, or a range of many orders of magnitude in semi-major axis and a range of many orders of magnitude in mass. Now, we also know that somehow these planets are formed out of things that look like this, namely circumstellar disks. So we now know, or we've known for a long time, that circumstellar disks are the birthplaces of planets, and we now know that we have pretty good estimates for their properties. The particular disk here, HL tau, has a picture taken of it, was 100 AU. It's actually predicted in my thesis. Exactly. Completely luckily, as in fortuitously, but nonetheless, you gotta brag when you can brag. So now more to the point, we've seen these disks left, right, and sideways. And we know their properties approximately, and one way or another, we have to use those properties as a way to constrain the planet formation problem. So in a nutshell, this is the 30-second review of 30 years of work. The star formation process naturally produces circumstellar disks. The angular momentum and magnetic field problem in star formation, one way or another, conspires to make things at solar system sizes, not stellar sizes. The disk size you get is 100 AU. I just showed you bunches of observational examples of that. So the natural size scale you get is 100 AU. Now the mass that you have is thermostated to be approximately about 10% of the stellar mass. So the maximum mass that's stable is something like a tenth of the stellar mass, a tenth of a solar mass typically. Now, looking a little bit finer, we see that there's a surface density that gives you this mass. It's generally considered to be a power law. There's lots of observations that don't all agree with each other, but it's more or less a power law with an index anywhere between 1 and 2, depending on exactly what question you ask. And finally, we know that these disks don't live forever. They live much longer than the star formation problem. The star formation process itself takes about a tenth of a million years, maybe a couple tenths of a million years to actually assemble the actual stellar mass, because m dots are 10 to the minus 5 solar masses per year. But the disk lasts for 3 million years. Now, they don't all last 3 million years and then die. There's a distribution with a characteristic time of 3 million years, and that will become important in the second half of the talk. Now, we also know where the planets occur. The very first giant planets were found were hot Jupiters, so everybody said, oh, all of a sudden planet formation happens at 4 days or 10 stellar radii. Well, it turns out that those are rare events. They're just the easiest to see. Now that we actually know where the planets are formed, we can plot the occurrence rate as a function of period or semi-major axis. And guess what? The occurrence rate tends to peak at 3, 4, 5 AU. Here's several more compilations of that. In other words, giant planet formation happens at the ice line, just like we said in the 80s. And the reason why we said it in the 80s was not because we were smart. It's because it's obvious. That's where the mass is. So we want a theory of planet formation that predicts or postdicts the formation of planets right at the ice line, okay? So planets form at the ice line. So there's 2 ways to make planets. In principle, you can make them from top down through gravitational stability, or you can make them from the bottom up through core accretion. Let me talk briefly about gravitational instability and tell you why it's not what I'm talking about today. Gravitational instability is great. Caitlin has done some great work on this, and it's very important. It's just not very important for the next hour, okay? So the very first simulation that I know of was actually done by Willy Benz right before he moved here, where we were trying to make binaries by gravitational stability. And when you try to make binaries by gravitational stability, you naturally don't get binaries. You get brown dwarfs. And what you get is objects that gravitationally become or form out of gravitational instability with typical masses of 10 to 30 Jupiters, and they tend to butt up against the outer half of the disk, so they live at 50 to 100 AU. So the very first simulations showed that you basically get brown dwarfs at 100 AU. Now, this was terrible, terrible numerics. Caitlin's done some of this, Andrew's done some of this, Jean Zhu, which many of you know, did a much better job than we did. And guess what? He found brown dwarfs at 100 AU. When you look at things in the sky with image planets, you often see brown dwarfs at 100 AU. So what I would like to argue is that when you form objects through gravitational stability, you form brown dwarfs at 100 AU. And that's important if you're trying to form brown dwarfs at 100 AU. But what I want to make clear here is that a brown dwarf at 100 AU is not a Jupiter at 5 AU or 3 AU, okay? You can never, almost never get gravitational stability to make a bona fide object really as small as Jupiter, and certainly not as small as Saturn. And you tend to make them at 100 AU, not at the ice line. So we need a different process. And to put what I just said on the board, the gravitational instability makes objects in this box, namely prime dwarfs at 100 AU. Those nicely are coincident with the planets we see through imaging. So it's an important part of the process, but not where most of the planets form. I'm also not going to talk about the low mass planets. I want to have a theory that explains all of these. Now, in reality, I'm only going to probably explain some of these, but we'll see how far we get. Okay, so here's the core accretion paradigm. We basically want to build planets from the bottom up. Now, conceptually, we can break this process into 3 stages. The first stage, which is ingeniously called stage 1, is where you make rocks and you build them into a larger body. And the body will grow with largely a heavy metal composition up until it's about 10 Earth masses in size and mass, okay? Now, at that stage, it's finally big and bad enough, has enough gravity to hold on to some gas, and it will start to accrete gas. And then the object enters into phase 2. During phase 2, the object slowly gathers gas. But when the planet's in this stage, the gas is very tenuous and very puffy, and it has a hard time cooling. So it fills the Hill sphere. And it fills the Hill sphere such that it becomes difficult for more material to enter the Hill sphere and thereby become part of the planet. And it has to wait until the stuff that's already there cools and contracts a bit before more stuff comes in. This is actually kind of this problem has been studied. Andrew did some nice work on this about 10 years ago, but there's still some subtleties of it. We don't fully understand exactly how this works. But what we think happens is that once the atmosphere gets sufficiently massive and self-gravitating, the gravity of the atmosphere pulls it together to the point where more stuff can come in. And then material enters the Hill sphere and we reach a runaway accretion phase, okay? And that's the 3rd stage. So in pictures, we have stage 1, the formation of the rock, stage 2, a hydrostatic object that's puffy, and stage 3, lots of stuff comes in. In terms of the time scales and mass scales, we don't know exactly how long each of these takes, but it's relatively short, as in less than 1 million years to form the 10 Earth mass core. It takes a long time, namely a couple of million years or longer, for the object to become massive enough for the atmosphere to allow rapid accretion. And then stage 3 happens kind of sort of rapidly, as in again, of less than 1 million years or a quarter of a million years. We don't actually know. People have built models, and there's a lot of discussion we can have afterwards. Okay. Now, what you see on the scale is that this is a log mass scale. So 10 Earth masses come in phase 1, another 10 Earth masses come in phase 2, and then 300 or 3,000 come in stage 3. I'm only going to talk about stage 3. I'm only going to talk about this late stage when all the mass is coming in. The reason why I'm doing that is because that's where all the mass comes in. And it's also where we might actually be able to see these things. Okay, so what we're going to do is we're going to look at stage 3. And the goal of what I'm going to show you next is to describe the stage 3 as completely and analytically as I can. And what you're going to find, to give you a preview of what you're going to see, is that the material that's entering the Hill sphere is rotating. It's rotating at something akin to the mean motion of the planet, because the planet's going into orbit, right? So it can't be not rotating. And because of you have angular momentum, it will fall not onto the scale of the planet, but rather onto the size of a circumplanetary disk. So all of the action has to be in that circumplanetary disk. Most of the material falls onto the disk, not onto the planet directly. So what we need to do is we want to find solutions as a way to describe the material coming from the Hill sphere onto the circumplanetary disk. We want an analytic description of the infall region. Then we want a description for how the disk itself evolves. And it turns out that the inner disk is truncated by magnetic fields, just like in the star formation problem, and we need to take that into account. And then once we have all these pieces in place, we want to calculate the spectral signature of these to see what they look like. And then the luminosity, as you'll see, has several different contributions, and we can find the spectral distributions. So the first paper we wrote on this was a couple of years ago. We didn't have anything better to do during COVID, so I wrote this paper. There's 3 generalizations that have subsequently appeared with my student Astor Taylor, and then a recent paper I just posted a couple of days ago in honor of my trip here, where Constantine and I generalized this further, because I wanted to get it out in time for this seminar. So we did. Okay, so this is just a picture. And one complication that you might worry about, there's actually 4 outer boundaries. So there's the Hill radius, which is one way to describe where the material, the boundary between where the material belongs to the planet and belongs to the background circumstellar disk. There's also the Bondi radius. There's the astrodynamical sphere of influence that most people don't know about, but Renu probably knows more about than all of us combined. And then there's the disk scale height. So in general, the smallest of these is the relevant outer boundary condition. And for the parameter space that I'm worrying about, the Hill radius is the one that matters. Once you get to the point where you're in this rapid runaway accretion phase, the Bondi radius is generally much, well, at least significantly larger than the Hill radius. So the Hill radius draws the boundary. At the very, very, very latest stages, once the planet gets really, really, really big, it can pop out of the disk so that the disk scale height becomes smaller than the Hill radius. And then outflow or inflow, rather, can only take place along the equatorial directions. We can deal with all of these complications for the sake of the next half hour. I'm only going to say Hill radius, just instead of giving you more answers to everything. So just be aware there is this complication, okay? So let's just jump to results. If you have a flow, m dot coming in through the Hill sphere in a spherically symmetric manner, you can calculate the orbits of the material that's entering the Hill sphere and spiraling in towards the disk. As we'll see, the disk is a small fraction of the total mass, so the potential is very well described by a point potential of the planet. You can also show, it's not 100% obvious, but you can show, and I will argue, that as you come in from the Hill sphere, the gravitational forces dominate the pressure forces, and the farther you fall into the potential well, the more they do so. So I'm going to show you results with only ballistic trajectories. In the simplest version of this problem, where I have 0 energy orbits tied to infinity, which is basically the Frank Hsu solution, which was generalized by Casson and Moosman back in 1981. You get velocity fields that look like this, and you get a density field that looks like this. The projections of the streamlines coming in look like this picture, and you form a disk at some radius out to what's called the centrifugal radius, which is 1 in this case. And in the simplest version of the problem, the centrifugal radius is exactly 1/3 of the Hill radius. That's what you get when the rotation rate at the Hill radius of the material coming into the Hill radius is exactly the same as the mean motion of the planet. So that's your sort of default case. There's a more complex argument that says you can have what's called an angular momentum bias, where the angular momentum is actually somewhat less than that. And we can take that into account. The formulae get messier. Now, these are messy enough, so what you need to know is that in rough terms, if I take that non-spherical density distribution and spherically average it, the density goes like r to the -3/2 at large distances, which means outside the disk. And then the inner part, it's less steep. It goes like r to the -1/2 or so. Now, we have a disk which obeys a disk evolution equation, and there's a source term, and the disk is sourced by this previous infall that I just described. There's a density and a velocity field that tells you how much stuff falls where on the disk. You put that into the surface density distribution of the disk, and then you solve it, and you get 2 different ways to do it. You can do what I call the bucket approximation, which means you imagine the disk is just a bucket and stuff falls onto it. And that tells you where stuff falls. That's the top solution, which is the dash curve. If you then assume that you have viscosity, this viscosity will in steady state rearrange that into a surface density. And depending on what the viscosity is, you get this form, which depends on the size of nu. And as you make the viscosity larger, you make the standing population of material in the disk smaller and smaller. The point is that you have solutions for that. And what you need to know is that to 0th order, they're all 1/r. That's for a standard alpha viscosity. If you change the viscosity, you have to change that accordingly, but it just shows up in the coefficient, so it's very easy to change. But for the standard results of what you think alpha viscosity is doing, surface densities look like 1/r. And if you have an appreciable alpha, like 10⁻�3, the amount of material in the disk is quite small compared to that of the planet. Now, if we look at the inner boundary of the problem, we have magnetic fields. Now, interestingly here, there's something new for those of you who know the star formation result. So pay attention, Andrew. In the star formation problem, we have what's called the magnetic truncation radius, where material is accreting through the disk, and it reaches a point where the ram pressure of the stuff coming in through the disk is matched by the magnetic pressure of the field lines from the central object. In the star formation problem, that's the star. In this problem, it's the planet. It has this crazy 1/7 dependence. And this is well known in the star formation problem. It sets the inner boundary for disks around stars. In addition to that, there's actually another interesting scale, which is a capture radius. There's a field line such that there's a streamline that intersects it at the horizontal point of the field line, such that the field pressure here is matched by the ram pressure of the incoming material there. So any streamlines that fall to the left of this matching point will hit the streamline and come in here. Anything that passes to the right will fall back on the disk. So the actual capture radius of the planet is somewhat larger than it would be otherwise due to the magnetic fields, and we can take this into account. Now, for purposes of actually seeing these things in the sky, both of these scales are just a couple of Jupiter radii, and that's way smaller than the disk, which is smaller than the Hill radius, which is tiny compared to the disk, circumstellar disk. So this is way down in the weeds, so you won't actually see it observationally, but it's interesting that it exists.
Sorry, Fred, why is this new for the planet formation problem and not in the stellar problem? What makes
Oh,
it?
no one's ever done it for the stellar problem.
But in principle, is there some reason why it's not relevant, or you just?
Oh, I don't think anyone's ever asked that question before, so. No, I think it could be relevant in the star formation problem, it's just that no one's ever done it, so.
Why didn't you do it in 1993?
I didn't think. I was probably doing something else. So, good question though. So moving on, what we have here is we have this paradigm or this formulation where I can calculate the velocity fields, the orbits, and the density fields of the incoming material. I can use that as a source term for what hits the disk. I can then solve for the surface density of the disk. I can use the magnetic fields to solve for the inner boundary. And I can basically calculate completely analytically the entire structure of this forming planet during phase 3. Now, in order to do that, I have to specify these four things. I have to tell you what the current mass is. I have to tell you where the planet is because I've used the mean motion to set the rotation rate. I have to set the mass infall rate, and I have to set the field strength because the field strength tells you how those inner boundaries work. The inner boundaries are so small that the magnetic field strength doesn't actually affect anything unless you care about the actual accretion onto the planet, and there could be line emission that you care about there. But if you don't care about that, it's only the first three that matter. Now, in a complete theory, I would actually know how the mass of the planet grows with time and how m dot changes with mass, and I could do evolution. The time scales are such that the time it takes to fall from, you can just kind of do this in your head, the time it takes to fall from the Hill radius to the disk or planet is going to be, what's it going to be? It's going to be years, right? Because it's the orbit time, which is a few years. And this whole thing is taking place over 1 million years. Point being, a year is less than 1 million. So because of that, I can take the instantaneous mass and instantaneous mass infall rate and calculate the structure instantaneously. If I have a theory that gives me m as a function of m dot or whatever, I can just use these same formulae and just put that in after the fact, because it's all because of the dispatch and timescales. Now, this is sort of what I would call the simple vanilla picture, and that's what I've given you results of. These 3 subsequent papers that we wrote after COVID generalize this in several ways. As I mentioned earlier, the rotation of the outer boundary need not be exactly the mean motion of the orbit. You can put in an angular momentum bias. Instead of using 0 energy orbits, you can choose different energy orbits at the Hill radius. That gives you more complicated orbits, more complicated density distributions, but you can do that too. When the infall comes into the Hill radius, it's not necessarily going to be spherically symmetric. The numerical simulations of people trying to do this, in fact, show that it's not spherically symmetric. The problem is, some argue that it comes in primarily along the poles. Others say it comes in primarily along the equator. And of course, Doug Lynn has a paper that says it comes in at mid-latitudes. So the numerical people tell us, well, it doesn't come in spherically symmetric, but they don't agree on what that spherical distribution is. So what you can do is you can use a different angular distribution of infall. You can go like cosine squared or cosine or 1 or sine squared and do all the algebra again and get results. And finally, the disk has an outer boundary. The natural place to put the outer boundary is actually at the Hill radius, because that's the boundary between what belongs to the planet and what belongs to the background circumstellar disk. But the disk can't actually extend quite that far out, because once you get far enough out, 3 body effects, or however you want to say it, lead to chaotic orbits that cross. So the disk is actually not a disk once you get far enough out. Steve Lugo calculates that to be at about 0.42 of the Hill radius, so about half the Hill radius. So you have to put in another boundary condition. Miraculously, you can actually generalize the equations I showed you, which are messy enough, to include all of these complications that still get analytic forms. That's on the paper that I just published or posted a couple days ago for all 0 of you who want to actually look at this. But they're there if you care. Okay. So given all that, the question is, what do these things look like? Okay, so you have a disk around a planet in the middle, you have an infalling envelope of stuff, and then you have photons that are working their way out. So how do we make sense of how this looks? Okay, so the first thing you have to do is you have to specify what the luminosity is. Well, it turns out that there's a bazillion different luminosity contributions. So let me just give you them in words. You have direct accretion onto the planet, which leads to shocks and the generation of energy. You have direct accretion onto the disk, which leads to shocks on the disk and luminosity. You have the mixing luminosity. Remember, I said the material that comes into the disk doesn't actually know in advance it's supposed to be part of the Keplerian rotation curve. So when it gets there, it has to adjust its angular momentum. Well, it doesn't adjust its angular momentum, it keeps its angular momentum and adjusts its energy accordingly. Basically, it moves into the potential well a little bit, giving up energy. So there's a mixing luminosity. There's actually a corresponding mixing luminosity on the planet, which is impossible to calculate. There's the viscous dissipation within the disk. And then there's, in principle, the planet itself can have an intrinsic contraction luminosity. So there's all these different luminosity contributions, all of which we can calculate. And what you get is you get a black body light spectrum for the planet itself, and then you get a disk, which gives you an infrared excess. Depending on where you put the inner boundary, which depends on the field strength, you get slightly different curves. These are the spectral energy distributions here for the simplest case, where I'm just showing you the planet and the disk, not the envelope. There's an envelope around it which will eat these photons and re-radiate them, and we have to do the radiative transfer problem to see what those look like. This is not that. This is that. Okay, so the simplest way to do that is to take the non-spherical density distribution that I showed you and then spherically average it. And then if I further assume that the envelope is optically thick, or at least partially optically thick, to the photons from the central object, namely planet and inner disk, but it's optically thin to its own emitted radiation, which is actually a pretty good approximation, and I'll justify that in a minute. Then you can actually write down an analytic form for the temperature distribution by integrating over that whole envelope. And you can have a completely analytic description of the spectral energy distribution, which is shown here. I call that the spherical cow approximation. And you see you have the green curve is the planet and disk, and then the envelope is this curve, and they add up to be this curve, okay? Now you might worry, well, this is kind of an extreme approximation, especially when the density distributions look like this. They're not that spherical. But because it's optically thin to its own emission, you can get away with a lot of sins. And here's what the result is. If you take one of these typical models, so something that has the mass of Jupiter and a mass accretion rate of 1 or 3 Jupiters per million years, if you use the spherical envelope approximation that I described, the completely analytic treatment is the green curve. If you use a ray tracing curve, you get the red curve. And if you use RAD 3DMC, a Monte Carlo curve or code, you get the purple curve. There's a little bit of mismatch here, but that's actually because RAD 3DMC doesn't let you put in exactly the same disk that the other two models have. So that's actually a problem with the code, not with the approximation. Point being that in this part of parameter space, all 3 methods give you, within the width of the lines, the same spectral energy distribution. Now, there are parts of parameter space where that's not true. So subsequently, I had my student Aster do both RAD 3DMC and some other calculations to give you non-spherical results. In the interest of time, since I want to get to the second half of the talk, what I'm going to do now is just show you the equivalent spherical envelope calculations. And this will give us a way to understand how the spectral energy distributions depend on the initial or the fundamental parameters that describe the system, okay? So here we go. Remember, there's basically 4 variables you specify to specify what is your planet. The mass accretion rate, the semi-major axis, as in where it is, and the field strength, which sets the inner boundary. So if I fix m dot at 1 Jupiter per million years, I fix the semi-major axis at 5 AU, and I fix the inner magnetic field strength at 500 Gauss, I can then see how the spectral energy distributions vary as I vary the mass. So not surprisingly, as the mass gets bigger, the thing gets more luminous, but you see that it also gets bluer. So as I increase mass and constant mass accretion rate, I get brighter and bluer. If instead I fix the mass and I increase the mass accretion rate, again, not surprisingly, it gets brighter, but it gets brighter and redder because the optical depth of the envelope grows. Fun fact, for a given m dot, the optical depth of the envelope gets smaller as m gets bigger. We kind of knew that from the star formation problem, but it actually shows up here in exactly the same way. If I say, well, what happens with field strength? If I add more field, I increase capture radius and the m dot, and I get more stuff falling onto the planet, which gives me more blue photons. So I get a little brighter and a little bluer, but it's not nearly as big of an effect as we saw in the previous cases. And finally, what if I move the planet around? If I move it in and out, I change all the variables accordingly. As I move the planet inward, the spectral energy distributions get narrower. And that's because the dynamic range between the planetary surface and the hill radius gets narrower. So I have less of a temperature range and a narrower spectral energy distribution. Now, where we are in observational space is we're just beginning, okay?
Sorry, can I ask you a question? Because I find it very interesting, but I'm a little confused on what sets the temperature of the envelope. Is the location of the planets and therefore also irradiation from the star? Or what is set?
What sets the temperature of the envelope is the radiation from the central planet and disk.
So it's the combined.
Yeah.
That's why as you move closer in, it's also hotter.
Well, there's that, but the biggest difference is that as you move closer in, the dynamic range of the envelope, the Hill radius is smaller. So the ratio of the Hill radius to the Jupiter radius becomes smaller as you move in. So that means that the range of temperatures sampled by the envelope gets narrower, and then the spectral energy distribution gets narrower. In the limit that it goes to 1, you get a perfect black body, right? And you see that if I'm at 1/10 of an AU, I'm actually kind of sort of close to a black body. It's actually a little wider than a black body, which is hard to see on this plot, but you're getting narrower and narrower. And that's just geometry, really. Now, one of the things you could have asked me, which is very much related to this, is that what I'm showing you here are the spectral energy distributions of the emission produced by the forming planet as it is radiated out of the Hill sphere. Now, if you put this in a disk, there could be stuff outside the Hill sphere between the Hill sphere and your telescope, and that needs to be taken into account. We have plots for that. If there's too much of it, you'll just attenuate everything and not see anything. And that's an important concern. In fact, because of that effect, you're more likely to see these objects in the very, very latest stages after they've popped out of they're so large that the Hill radius is bigger than the scale height, and you have a attenuated envelope. In fact, the observational case I'm going to show you, I think, is one of those cases. This is sort of a larger planet at larger radius in a later stage than what I just showed you. And we have, 2 data points on this, right? So what we would like is we'd like to have spectral energy distributions for a variety of forming planets with lots of masses and lots of disks and whatnot. And we've basically got the first couple of data points now. There's a few other claims of the detection of forming planets by Chugno and a few other folks as well. But this whole business is very much in its infancy. But the hope is that in the next decade, we'll at some point get a flood of data and we can start looking at planets while they form. And again, this particular case is probably a little bit later stage than what I've been telling you, but this is all we got observationally as of today. Okay, so to wrap up the first half of the talk, where are we? Well, we have an analytic description for the infall, which includes the velocity fields and the density fields. I can generalize that to a variety of different orbits and a variety of different angular momentum biases. We have an analytic description for the disk surface density, including the steady state viscous accretion stage. I can generalize that to include angular momentum adjustment, different source terms, and so on. I've introduced a new magnetic radius. I've introduced the different velocity or luminosity contributions. And for this whole picture, we can calculate what the spectral energy distributions look like. We could do it analytically, which is primarily what I showed you, but my student Astra has gone and done the numerical things in 2 subsequent papers, which I will not show you spectral energy distribution after spectral energy distribution, but we can do that. They don't look that much different, which is why I'm not showing them to you. Now, we have solutions for instantaneous values of the 4 variables, but if you had a complete evolutionary theory, you could connect these and consider these as a function of time. There's actually a function of time beneath this little things. You can't see it. Now, one point I would like to make, at least some fraction of the audience has sort of grown up in the star formation problem. So it's interesting to contrast what happens in the planet formation problem and the star formation problem. In both cases, you have this rotating infall falling onto a disk. Most of the angular momentum, or all the angular momentum, is carried by the disk. Most of the material falls first to the disk and then onto the central object. What's different? Well, the big difference is this. In star formation, the outer disk edge is at something like 100 AU, and the inner disk edge at the surface of the star is like a couple solar radii. That's a factor of 10 to the 4. Okay? Star formation takes place on a time scale of 1/10 of a million years, maybe a couple tenths of a million years, but relatively rapidly. So you kind of have to, in your mind, go a factor of 10 to the 4 in radius in 1/10 of a million years if the disk is going to move the stuff, right? In the planet formation problem, the dynamic range between the outer disk edge and the forming planet is only a factor of 180 if you use the full disk. If you use the truncated disk and an angular momentum bias, it's only a factor of 100. So it's smaller. And it takes 3 to 10 million years to make a planet. So just kind of do the math without doing the math. Here you have a factor of 10 to the 4 to go in a 10th of a million years. Here you have a factor of 100 and you have almost 10 million years. It's a lot easier to move stuff in the planet formation problem. And what that means, I think, is that when you do star formation, the disk will load up and will go gravitationally unstable and give Caitlin something to calculate, right? Here, the viscosity can keep up. So I don't think these disks generally go gravitationally unstable because even a tiny bit of viscosity, 10 to the minus 4, is enough to keep you going. So it's a lot easier for viscosity to operate a circumplanetary disk than a circumstellar disk. Now, this whole picture is incomplete because we need to piece these pieces together and let the planets move around. We need to actually look at what the infall looks like as a function of time and so forth. But the biggest thing that we don't know is what actually stops mass accretion onto the planet. What I've shown you so far in the calculations that we've talked about so far is I've just said, well, let's take a mass and a mass accretion rate and see what the structure is. And I think that's a legitimate thing to do. But what you really like to do to understand all planet formation is ask the question, well, why does this ever end? Why don't you just keep accreting? So that leads us to the question, what sets the masses of forming planets? And how do I go about trying to calculate the distribution of planetary masses? I will say, I kind of believe the first half of my talk more than the second half of my talk, as in, I think the calculations are much further along and the physics is much more known. Here I'm venturing a little bit into the unknown, but I think it's a very important problem and it's worth doing so, but I do want to make you understand that. Okay, so to be honest, what ends the planet accretion process during the core accretion paradigm is yet to be determined. We don't fully know, okay? Now, one obvious possibility is the end of the disk. The disk will eventually run out of mass, right? Moreover, as I'm about to show you, the disk lifetimes are exponentially distributed. So my friend Michael Meyer, who also used to be here, says, well, Fred, obviously it's just the disk run out of mass. And I said, well, Michael, obviously you're wrong, because I always tell Michael that. Because if you have a constant mass accretion rate and an exponential distribution of lifetimes, the mass distribution, which is just m dot times time, will just be a different exponential. You're just changing variables. But we know that the mass function is not an exponential. So how does that work? So I said, Michael, I will prove to you you're wrong. And then COVID happened, so I had lots of time. And then I said, Michael, I can prove to you you're right. And what I mean by that is you have to turn an exponential into a power law. And I have a general framework to do so, which I'm now going to show you. So first of all, what do I mean when I say that the lifetime is exponentially distributed? Well, if I look at the frequency of disks as a function of age of the star forming environment, I get a function like this, and Jesus Hernandez is my go-to plot on this. There's about a half a dozen others that show the same thing. You can plot, you can assume that you're making an assumption here that all the disks in all these regions are kind of behaving from the same parent sample. And if you do that, then this exponential distribution is also the distribution of the lifetimes. And I'm saying that it's an exponential. Let me try to justify that. I can plot various exponentials on these data points. The boxes are just the same data from the previous thing where I've gotten rid of the error bars to make and put the boxes in instead. And you can do it in a log way or a semi-log way. And or not a linear way rather. And it's not exactly an exponential, but it's kind of close enough for government work, okay? And the half-life is something like 3 million years, okay? Now, one of the things you need to understand is that when we say the half-life is 3 million years, that doesn't mean all the disks live 3 million years. At 10 million years, 10% of them are still there. A lot of people fail to realize that. So keep that in mind. Okay, now what about the observational situation for the mass function for planets? Well, back in 2008, Andrew Cummins had this plot where he tried to calculate the mass function for planets. This is a log scale. So a flat distribution in this histogram is a 1/m dPdm distribution. And what you see is it's pretty flat with a deficit in the last bin. If you fit a power law to it, the best fit is something like 1.3, but it's not a great fit because it could be plus or minus 0.2, so it's 1.1 to 1.5. And it's over the range of 10 Jupiters down to a third of a Jupiter. So almost 2 decades. And this is 2008. If you dial yourself forward to 2021, what you see is that we have a logarithmically distributed histogram. So flat is 1/m. It's flat except for the last bin where there's a little bit of a deficit. The fit is not great, but it's, you fit with the power law, you get 1.3, but it's not great, so it's plus or minus 0.2 again. Okay, so after 13 years, we got the same exact answer. So I'm going to assume that the mass function is power law with the slope of something like 1.3 or something. Now, if you look on the greater scale with the microlensing people, you see the stellar mass function, a planetary mass function, then who knows what happens at really small masses. The giant planet realm we're talking about is here, and again, you see a power law that has a slope of about 1/m. Lots of uncertainty, but it's all consistent with a mass function like that. So one way or another, we have to turn the exponential distribution of disk lifetimes, which is the lifetime over which you can accrete, into a power law distribution. This is our core accretion paradigm, where we have stage 1, stage 2, and how the heck does stage 3? So I've already made this argument. If you just have a constant m dot and you multiply it by time, since time is distributed exponentially, the mass function would be distributed exponentially, but that's not what we see. So our theory has to be more complicated. So here's our theory. The final mass of the planet is equal to the mass at the end of phase 2, which I'm calling M2, plus an integral where I integrate m dot from the time M2 to the end. This is exact. We don't know what to put in, but it's exact, right? It's true by definition. You start at M2, and then you integrate everything you get after M2, and that's your final mass, okay? Now, here's the beauty of the exponential, okay? We need to know what T2 is and what T end is. T end is the total lifetime of the disk, which we're thinking of as an exponential based on data. But here's the beauty of an exponential. If I change my variable from t to t wiggle, where t wiggle is t minus t2, in other words, I'm only measuring time since the end of phase 2. That time is also exponentially distributed. An exponential is the only distribution that has that property, and you know this from radioactive decay. When you have a bunch of radioactive nuclei, doesn't matter where you started. If I wait one half-life, half of them are gone. But I can start later with a different number, and when I wait a half-life, half of them will be gone. So the beauty of the exponential is I know the distribution of not only t end, but also t wiggle, which is what I need, okay? Now then, t wiggle has an exponential distribution. I'm going to now assume that the m dot goes like some power of the Hill radius, and that kind of makes sense. Bigger planets should eat more mass. If you just use the area, P would be 2 because area is r squared. The general argument in this business is that in addition to that, there's an extra power of r squared that comes in due to shocks. So most people advocate that p should be 4. I could do the math for any value of p. I'm only going to show you the results for 4. And then in addition to that, I'm going to say, and you'll see how this comes in, that I can put in efficiency factors. That each time you have a disk and an m dot, only some fraction of it's going to end up in the planet. There'll be an efficiency, and that efficiency won't always be the same from system to system, from disk to disk, from planet to planet. So there'll be a stochasticity to this. I can put in multiple efficiency factors. I'm going to only show you results for one, just because we're running out of time here. So this is a picture again. Specifically, what I'm going to assume is that the mass accretion rate onto the planet will depend on the Hill radius to the 4th power, which means the mass to the 4/3 power. I have to set a coefficient in front, and then I'll have a stochastic variable which varies from system to system. I'm going to choose this to be a stochastic variable that varies between 0 and 1 just for convenience. And then this is the value I don't know. This is a constant which I have to set. I will get a different or mass function for each value of this. But this is the only unknown, okay? And what it means physically, it's sort of the bare mass accretion rate during phase 3 after I've scaled out the mass dependence. Now, just to confuse you, when I present the results, I'm not going to present it in this form. I'm going to multiply it by 3 million years, namely the half-life of my distribution, to give you a mass scale instead. But it's still the same variable. It's only one variable. I'm just changing the name of it to confuse you, okay? So, a little bit of math. For that case, you can integrate the differential equation, and the mass as a function of time has this form. You can define a mass scale, which is sort of complicated, and then you can find the distribution of C, and you know the distribution of T wiggle, it's exponential. You can then do the math, and you get a mass function which depends on mass to some power, and an exponential integral which depends on T star, which also depends on mass. Now that's not very enlightening, so I'm going to show you the picture. Before I do that, let me just say I took the previous thing I showed you, I got rid of the stochastic variable and I multiplied by the half-life of the exponential distribution to give you a mass scale. That way I can give you a mass function as a function of this one variable. And here's what you get. As I make the mass scale larger, I go from green to red to blue. The mass scale goes from 1 to root 10 to 10 Jupiters, which means I'm making the mass infall rate bigger and bigger. And once I get to about 10, I'm kind of indistinguishable from the power law distribution that we see in the observations. So this paradigm of using basically 3 ingredients, a stochastic variable, an m dot that varies with m, and an exponential disk lifetime, can in fact reproduce the observed mass function, as long as the base rate of the mass infall rate is big enough. Now that actually makes sense if you think about what we're doing physically. If you make the mass accretion rate too slow, what happens? Well, suppose you make it longer than 3 million years. Suppose you make it 3 billion years. Well, then all of your action will happen because you're running out of disk in the exponential, because the lifetime has an exponential half-life of only 3 million years. So you need a fast enough m dot to be faster than the disk lifetime. Otherwise, you'll just reproduce the exponential, and then your curve will be too steep. Now, for other reasons, you can't speed up the problem too much. If you make the mass accretion rate too large, one, the circumstellar disk can't actually feed material to the disk that quickly, but also, this is a separate problem that I haven't done I did do a calculation, I don't have slides for. If you make the m dot too large, then you make the optical depth of the envelope too large, and then the the forming planet cannot cool. And if it can't cool, then the ballistic trajectories I showed you at the beginning of the talk no longer apply. And what you get instead is you get a puffy thing that doesn't actually let any material into the hill radius. So there's a limit on how large you can make the M dot and still have cooling. This is actually the analog of Martin Rees's 1976 paper where he calculated something called opacity limited fragmentation. He showed that in the interstellar medium, you can't make an object collapse to a mass with a mass scale less than about 10 Jupiters is what he got at the time. Otherwise, it can't cool fast enough to continue collapsing. So when you're forming a planet, you can't feed material into the hill radius too fast, otherwise it can't cool and collapse. It will heat up, and then if it heats up, it doesn't collapse, and then you don't have it. We see that in numerical simulations. If people do numerical simulations with an adiabatic equation state, it just heats the heck out of it, and stuff doesn't come in. If you make it isothermal, then you form a disk and you get the picture that I showed. So when you have successful planet formation, one way or another, you have successful cooling. So M dot can't be too larger, which means M can't be too much, M naught in this scheme can't be too much larger than the value of 10 that I'm using here. So we kind of know where we are on the scale. And you have to have about these parameters to get the right answer, okay? So to recap, the ingredients that go into a successful planetary mass function are we need an exponential lifetime distribution, which we see. We need an M dot, which increases with mass, and at least one random efficiency factor to spread out the distribution. And then we can turn the exponential into a power law. We can not only get a power law distribution, but we can get the right power law distribution. Now, if you believe all of this, and I said this is on slightly less strong footing than the previous part, then I have one more piece of land in Nebraska to sell you. You can do this all as a function of host mass. And if you believe that, then what you find is that the sweet spot for making giant planets is actually something close to a solar mass. If you have too low of a mass for the host star, you run out of mass before this whole distribution can be filled out. If you have too high of a mass of star, then the disks don't live as long and you run out of time before this whole distribution can be filled out. So the prediction is that once you get to too high masses, the mass function will become steep and you don't have any big planets anymore. And once you go to too low masses, you don't have enough mass and the high end of the mass function will also not be filled out anymore. That's much more speculative than the rest of what I've talked about. Now, everything here is simple. There's a number of complicating factors, competitive accretion, planets move around, and so on, that should be worked out. This is sort of just the first step. It gives us a framework to start working on the planetary mass function. It's not a full solution to what the planetary mass function looks like. Okay, so to conclude, I think I'm just about out of time. I would argue that most giant planets form through the core accretion paradigm. Gravitational instability produces brown dwarfs at 100 AU. The core accretion paradigm produces Jupiters at 5 AU. We've successfully, I think, constructed analytic descriptions for most of the pieces of the phase 3 of the core accretion paradigm. We can calculate the orbits of the material coming in, we can calculate the velocity fields, the density field, the envelope structure, the surface density, luminosity, and the spectral energy distributions, all to varying degrees of approximation. We could then generalize this to include different angular momentum biases, different orbits, different outer boundary conditions, different geometries. And then we can use the same paradigm to calculate the distribution of planetary masses. And it more or less works. You can turn the exponential into a power law, but you have to be careful about it. So there's 5 papers, I guess, you can read, should you actually care. And I will put up my conclusions and take further questions.
So we are very close to the top of the hour, so if people have to leave, please feel free to do so. But we will have time for this room and also set up the Zoom meeting for another at least 15 minutes. So for people online, please, if you have questions, please type them in the chat or raise your hand. Do we have any question in the room?
Don't be shy.
I was just wondering, so you seem to suggest that, okay, planet formation happens just at the snow line, mostly at the snow line, 5AU,
No,
preferentially?
well, let me clarify. The observations show that the planet occurrence rate peaks at the snow line.
Yeah, I know, I'm the second author on that.
Oh,
I know that. So, but the point is, what is your view on forming these giant planets further out, for instance, at distances where we see these rings observed by
okay.
ALMA? So,
Okay,
how would that work?
okay.
The ear radius is larger, so.
So I think I know what you're asking. So the original argument, the argument we made way back in the day was that the following, that the farther out you go on the disk, the harder it is, okay? Even then, we didn't know the disk lifetimes, but we suspected they weren't forever. You only have so many millions of years before you're gonna run out of gas to make a gas giant, so you're gonna be compromised. Now, the further out you go, the slower the clock runs. If you want to build little tiny rocks into big rocks, the thing that matters most is the surface density of solids. And the surface density of solids decreases as you go outward, so it's easier to build the further inward you go, the harder it is, the farther out you go. Okay, so that argument says the closer you are to the star, the better. But if you get too close to the star, there's not enough mass. And if you get too close to the star inside the ice line, then the little rocky things that are trying to stick together are bare instead of have ices on them. I live in Michigan. It's easier for me to make snowballs than for you guys in Tucson to make sandballs. Right?
Yeah.
So the argument is that you want to be as far in as you can, but still have ices, which is at the ice line. And that's why the ice line was allegedly the sweet spot for forming planets, and that's pretty much what you see. Now, that doesn't mean that's the only place you can see them, because once you made the big core, it can be moved in a little bit, and it can eat gas at 1 AU just as well as 5 AU. It can even eat gas at sometimes at 0.05 AU, where the hot Jupiters are. It's just that it's easier at the ice line. The farther out you go, the harder it is, because everything just takes longer. The orbits are longer, everything takes longer. And you're going to run out of time eventually. So I think if you take everything I'm saying at face value, which you probably shouldn't, but if you do, you would predict that if you could calculate the mass function at 5 AU and 10 AU and 30 AU, the mass function should be steeper at 30 AU than at 5 AU, because you'll have a deficit of the biggest planets, because you run out of time before you get there.
Question from Leon from online audience. Leon, do you want to speak out?
Hear me?
I think we cannot hear you very well. Let me check.
Okay.
Oh, now it works.
Can you hear me?
Yes,
What?
now we
Yes.
can hear you.
All right. Hi, Fred. Thank you for a nice talk. So you mentioned how the planet mass distribution function will scale with this mass of the central star somehow. Can you comment if you have thought about how this will scale with the metallicity of the central star, since we have some data showing the correlation between giant planet formation and stellar metallicity?
I don't have a good answer for you. That's a very good question. We did not do that calculation. We have sort of a, I'll call it a half-assed calculation of how to do it with how the mass function should vary with the host star mass. We do not have one for the metallicity, but I will try to think about that. That's a very good question. So what's the observational sense? What do you see as you go to high metallicity? What does the mass function do?
More giant planets.
Well, you have
Well, there's two things. There's the occurrence rate and there's the steepness of the mass function.
Oh, that we don't know, I think.
Well, I'm talking about the steepness of the mass function. The occurrence rate goes up.
Yeah, the current rate goes up, but
Okay.
I don't think we know what is
Okay.
the mass, how the mass.
Okay,
function.
it'd be nice to know.
Make
But
your
you have
prediction
seen the
now.
data, there isn't much data.
What's that?
Make your prediction now before they have their
Yeah.
data.
Oh, yeah,
Good
I
time.
probably should think about it before I make a prediction.
So I have a question about free floaters.
Free floating planets.
Free floating giant planets, which
Yes.
apparently exist. We
Yes,
have
they
examples.
apparently do, yes.
Yeah, and so are they escaped planets in your scenario, or what are they?
Well, I think there's three things that could go on. One is that when you have giant planets forming in any scenario, it's possible, especially if the surface density of solids is really high, that you get lots of planets. And it's quite possible for the system to grow planets, but so that they're stable on a, let's say, 3 million year time scale that I'm making the planets, but they're unstable on, let's say, a 30 million year time scale, in which case some planet's going to get kicked out. So one source of freely floating planets will be internal scattering, where I have planets forming in a disk that gets too crowded. It has to be rarefied enough that I can make the planets in the three, so it has to be stable on like a 3 million year time scale, but still unstable on a longer time scale, so I eject them. Now, that will eject the smaller freely floating planets, because the smaller ones are the ones that are preferentially kicked out during the dynamical scattering interaction. Another way to freely float planets, or produce freely floating planets, is to imagine I make lots of brown dwarfs at 100 AU, like in the gravitational stability paradigm, and then I put those solar systems in a cluster. There will be dynamical interactions. I'm going to talk about this on Thursday. That's Thursday's talk, is what happens to star formation or planet formation or planetary systems in a cluster. And I'll give you the answer. Each cluster will give you 2 of them. In other words, there will be gravitational interactions of systems flying by other systems. On average, it will liberate a few planets per cluster through dynamical scattering interactions. That's probably not enough, but that is one channel, and it will happen only that often. The third channel is to basically just make either a star or a binary at some large separation or completely independent of another star, down to Martin Rees's opacity limited fragmentation limit. So you're making these freely floating planets basically as a little tiny star. Now, the third channel will give you the biggest objects. The first channel will give you the smallest objects. So if all these things are known. And I don't know what the duty cycle is of all 3 of them together, but I think you can form freely floating planets through all 3 mechanisms. Not a super satisfying answer. I can tell you're not super satisfied with that.
Hey, John, do you want to ask your questions?
Sure. Hi, Fred. This is Joan Najita. Thanks for the great talk. Very inspiring. So here's quick question. I understand that super Earths and Neptunes are very common kinds of planets.
Yes.
You know, every solar system might have one or more. What explains why they're so popular? Do they start forming really late and run out of time to accrete gas? Or do they form early, but stage 2 is somehow very long for some of these planets? Or maybe it's something else.
Well, that's a very good question. What I would say is that to 0th order, I would actually say what you said, only even stronger. To 0th order, every rock in a solar system is in a super Earth. So super Earths are just the natural thing that rocks tend to make. And that's why we see Kepler compact systems or Pisa-Pod systems with 4 super Earths all lined up in a row. Now you might say, well, what about our solar system? We don't have any super Earths. Well, we actually have 4 of them. They're in the cores of the giant planets. They just happen to eat some gas. In fact, all the rock in our solar system are in the 4 super Earths in the middle of the giant planets. There's 1 Earth mass in Earth, which is nothing compared to the 100 total we have in the solar system. And Mars doesn't even count. So all the rocks in all the planets are in the super Earths, just like you say. Now, your real question, which I don't have a great answer for, is why didn't some of them or more of them eat gas? Well, the ones in the inner solar system might be too hot to eat gas. The ones in the outer solar system might run out of time and eat gas. Basically, I would view giant planet formation through the core accretion paradigm as a race. You got to get through stage 1, which takes a while. You got to get through stage 2, which takes a long time, and then you have to eat gas. And at the same time, the disk is going away. So you have to win the race before the gas goes away in order to successfully make a giant planet. So it turns out, at least the data are telling us, that more often than not, we lose the race and you end up with just super Earth or some icy stuff on it if you're in the outer solar system, or some gaseous stuff if you're in the inner solar system, or even some water in some cases, but you don't end up with the full gas giant. I don't have a good quantitative answer to your question, but I think qualitatively what I said makes sense.
Great. Let's chat about that some more tomorrow. I just thought with all the AMLA results, planet formation was, a lot more successful than we were just discussing, but glad to chat more about that.
Yeah, let's talk tomorrow. Looking forward to it. Andrew had a question.
Yeah, I actually thought Leo was maybe going to ask a different question, because when you talked about the fact that this late stage accretion, that was the first part of your talk, that right, it is dependent on this ability of gas to cool, and
Yes.
lots of simulations find that it's actually very difficult to get the gas to cool. And not just when it's adiabatic, but as Leo and others have shown, when you try and include realistic opacities.
Yeah, you gotta cool,
So-
otherwise it doesn't work. That's clear.
So yeah, but I guess the question there is that, right, you built these nice models that assume ballistic trajectories that are in free fall, which may not hold if things are cooling limited. But if things seem very sensitive to cooling, then maybe things are in this cooling limit and the trajectories are not in free fall, and that could maybe change some of these solutions.
Oh, well, there's several things in there. You're right, of course. Another generalization, which I've worked on but didn't get a satisfactory result on, is to put pressure, partial pressure, into the orbital solutions. So I have bazillions of equations on that, but nothing that I'm willing to show you. But give me some time, right? You can only do so many things. So one could put pressure into it. The other thing I would say, in the way to defend this, is that if you can cool sufficiently, then, and you start the infall process, then as you get further down into the potential well, gravitational forces grow faster than the pressure forces if you're not adiabatic, as long as you can cool at all. And then the further down the well you go, the more you win. So once you get started, you're kind of okay. The other thing I would say, and again, this is only a partial answer, is that for the cases when you have successful planet formation, you must have cooling for the reasons that you just said. So my solutions only apply to the cases where you have successful planet formation. They do not apply to the cases where you don't have planet formation and you're adiabatic and you can't cool. But you would like a more satisfying answer to that as well.
Any other questions?
Up later, somebody.
No, we thank our speaker again.
To sign up.
You put down my